Yeah, thank you very much. I just put on this microphone. It sounds like it's working good and everybody can hear me. So I'm going to go through and explain, like Marie talked about, we're going to talk about what the status quo. This is what we're doing right now, of course. So, you know, Heidelberg Materials is a big company here in North America. You can see we have quite a few people that work for us. We produce you know, more than 10 million tons a year of cement, which means that we have carbon emissions of more than 10 million tons every year, right? And of course, we do some concrete. We have quite a bit of aggregate, and we are highly engaged. We're an international company, so we bring that international perspective to the table as well. So concrete, make no doubt about it, is a very sustainable product. So as you can see, it's more than 50% of everything we make on Earth, besides water. You've heard this much repeated factoid is beside water, concrete's the #1 thing. But I learned from Karen Scribner, who is a great proponent of limestone, calcine, clay cements, is that it is more than 50% of the volume of everything we make on Earth. And for that, because it's such a big piece of everything we make, we have a significant carbon footprint. It's only 7 to 8%, which is a pretty good payoff for 50% of everything we make. However, it's a significant number, and so we want to reduce that everywhere we can. People are very excited about timber and some of those materials, but honestly, there's no way to replace concrete in our in the built environment. If you wanted to convert just 25% of the market that for concrete to heavy timber or any other burnable material, then you would have to plant a forest the size of India, and you have to wait 30 years. And you could harvest that forest, and oh, by the way, I hope you plant another forest to follow it up, right? So concrete's here to stay. And we're, you know, the point is that we need to work hard to make it more efficient. It's very low energy, very low carbon associated with it. By weight, it's one of the very lowest carbon materials that you can use, because frankly, concrete is based mostly on aggregate. And aggregate, you pick it up off of the ground and it's ready to go. You harvest it from a quarry, and you screen it, you process it. There's nothing else to do with it. It's ready, right? So concrete is a very sustainable product. But the way that we look at it and the way that we evaluate any material is typically through a life cycle assessment. Almost everyone here in this room understands this, but if you haven't seen it, I want to go through it because it's always good to lay the baselines. So you can see here, when we evaluate a material, we're looking at this production stage, the A1 through the A3. And so the idea is that we're talking about all the work we have to do to get the material ready, move it around for the logistics, that's our A2, and then A3, manufacture the product, all right? So for cement, the key A1 and A2 started in the quarry, right? We're looking for calciums and silica-bearing materials for the most part, and we're going to harvest that from a quarry. So our A1 and our A2 begin here in the quarry. And then our A3 is the manufacturing process, right? So the big impacts for cement come from the manufacturing. The A1 and A2 are very low in carbon. If you look at an environmental product declaration, and it will, and some of them will list the A1, A2, A3. The A1 and A2 for cement is very low. The manufacturing process is very high. The reason that's so very high, and this goes through it, you can see here, here's our quarry to manufacturing to shipping at the end. These are the impacts associated with these different pieces of it. There's right there our calcination process. When we're heating limestone, we're driving off the CO2 associated with the calcium carbonate. We're recombining that calcium with silicates to make primarily calcium silicate compounds. Of course, there's aluminum and iron in there as well, but primarily calcium silicates. And in that process, we're calcining our limestone. Once we get up to about 1400 degrees C, or excuse me, 1400 degrees F, we drive off the CO2, right? We capture the calcium, the CO2 goes out of our stack. That's more than 2/3 of all the emissions associated with cement production come from that calcination. All right? And the neat thing about that, and it's a fact of life, sometimes we talk about it as a fact of life. The neat thing about it is that CO2 can be reabsorbed. And so when you're manufacturing products like concrete block and pervious materials, can absorb almost all of that CO2 back because it's released into the atmosphere. And if you have materials that are hungry to reabsorb CO2, that CO2 can be reabsorbed. I think I misspoke there earlier and got my terms a little mixed up. But the point is, this is where the big impacts are from calcination. And of course, burning fuels like we do to get to those temperatures is the other really big piece in our process. So when we're talking about concrete, we focus on cement because those are where the big impacts are. The way we manufacture cement and have it be a lower carbon material is, number one, we get better and more efficient at burning. That's the number one thing we can do. All of our processes, we want to get very efficient at those and reduce the CO2 associated with the manufacture of our clinker. Right? That's the first thing we do. The second thing we do is we reduce the clinker in our cement. Right? We're doing that through blended cements like Portland limestone cements. We can do that through other blended materials. Essentially what we're doing is cutting the clinker back, reducing the amount of clinker in our cements because that's where our big impacts are. And here's a good example. This is just a quickie bar chart that shows you. So traditional Portland cement, you can see, is almost 95% clinker, right? Portland limestone cements, we've reduced that by about 10%. This happens to be one of our our top performers for PLCs. And as you know, we all like to talk about our top performers. That's why EPDs tend to be our very best concretes, our very best cements. And then blended cements. This is you can get this cement right here in Philadelphia. We have a product right up the road near Reading, Pennsylvania, where they make a type 1S. And because it has 40% underground blast furnace slag, our clinker content is way down to about 56%. One of the lowest GWP cements available in North America, 531. So if you're trying to reduce your carbon footprint with your concrete, you can just use that cement by itself. You can buy a PLC and do the blending at home. You can have silos, you can have slag cement, ash, whatever those different materials are, right? So we're trying to reduce our clinker content. That's essentially our big push. And I'm talking so much about cement because, as demonstrated in this bar chart, it is where most of the impact is. Right? Most of the CO2 associated with your concrete will come from the cement, right? And I know that that's an old thing and everybody already knows that, but it's important to talk about. So people like us, Heidelberg Materials, we're changing the way we do business, and we are seeking very hard to make sure that our cements are very carbon efficient. We're trying to reduce the overall carbon associated with our cementitious materials we sell. These are the world's most aggressive goals for 2030 to reduce carbon. We're going to reduce our cement, the CO2 associated with our cements. That's going to result in about a 47% reduction overall, and we're looking to capture 10 million tons of CO2 through carbon capture and storage. So these are the big things that we and other people in the industry, we're not the only ones, right? The industry is responding in these ways. So the traditional way, what has been established and that we know works, and that is the most powerful tools we have available to us currently, are to be energy efficient, right? Reduce the CO2 associated with the clinker that we manufacture, reduce the amount of cements that we have in our concretes, or the clinker content essentially, in our cements by using SCMs, using blended cements, etc. And then the other thing that we can do is be better designers. Structural engineers in this room, you can use your talent, use your know-how, and be very efficient with the concrete that you build with. And there's nothing, if you don't have to put the concrete in the building, then obviously you're going to save that CO2. You're going to reduce the environmental impacts associated with that structure. So these are the levers we have to pull now. And, you know, carbon capture and storage is honestly the only way for us to get that CO2 back that we've released during calcination. Other than natural calcination or recarbonation that happens in block, like we talked about, and in concrete in general, carbon capture and storage is really the big lever that we have to pull. It's very expensive, it's very hard to do, and so the very first one that's going to be put into place is in Brevik, Norway. They're going to capture 400,000 tons a year. We're going to be doing this in Europe now, or you know, you can actually in Europe, you can actually buy the cement now. You can prepay or go into a purchase agreement, and you can identify that cement for your project. And so essentially your job will be essentially a net zero concrete, a net zero carbon footprint associated with that, because the cement is manufactured, cement is the same, and as the CO2 goes out the stack, it's captured, cleaned, scrubbed, separated, compressed, and then eventually put down into the ground for permanent storage. So that's carbon capture and storage. We're doing that throughout North America and the whole world. Then the very next one, the first full scale, will be in Edmonton, Canada. Those are our plans. We're hoping to have that operating in 2027. That'll be 1 million tons a year. After that will be Mitchell, Indiana, 2 million tons a year. Remember, we're trying to get to 10 million tons every year. So we've got to install this equipment and start capturing carbon in a very big way. And of course, all these materials, we're like many people, we have a low carbon, you know, product. So there's concrete, aggregates, etc., cement. But cement is, like we talked about, the big way. Slag cements is one of the very well recognized lever to pull, right? This is an SCM you should be familiar with. There's lots of good information about this that we can talk about at another time. Essentially, this is a waste product just like fly ash. It's something that would otherwise either go to the landfill or be used as an aggregate or some other less impactful place, and it's used to replace cement, right? We're reducing that clinker content in our concrete. Fly ash is another SCM that everyone is very familiar with. Who's heard that fly ash is going away? Good, it's not. We have 2 billion tons of fly ash that has been landfilled in North America that we are harvesting and we're beneficiating and we're making useful for concrete. You're right. I said, you know, no, you're not, but you're right. Fresh ash is going away. The coal burning power plants that produce fly ash are converting to natural gas, and they're converting to renewable energy, which is a fabulous boom. That's what we want to do. So those ashes that are fresh, that are created by burning coal, are going away. However, we burned so much coal for the past 50 or 60 years, and we put so much on the ground in landfills that there's a tremendous resource there. So we are going out into those landfills. We're identifying where it was great fly ash when they put it in there. We're reharvesting that, processing it, and making it ready for use in concrete. So it is going away, but beneficiated ash will go ahead and fill that gap. Some of the neat things that we're looking at that are coming up in nanoparticles and nanotechnologies fall in this category. In these newly developed materials, we talk about calcined clays a little bit. We can utilize ground glass pozzolans and other waste materials that are reactive when they're reduced in particle size. If you grind something fine enough and it's an amorphous silica material, it will be reactive typically in concrete, right? So that's where some of these other materials come from. We're going to talk a little bit later about materials like organic materials as well. So this is what's coming. This is what we're finding to do. We're taking concrete that is crushed concrete. Everybody's very familiar with recycling concrete. But the fines have always been a problem. The paste portion, the finest material that you get from crushing has always been a problem. We are converting that problem into a solution. We're able to make that, turn that material into an SCM or reuse it to manufacture cement. And that's a big part of the circular economy, right? So you're taking a material, you're crushing it up, you're either reintroducing it into the kiln to manufacture more cement, or you can turn it into an SCM and replace cement, Portland or Portland limestone cements, right? And then, of course, then there's very cool products, that like Eat Smog, photocatalytic cement. This is an award winner that won at the awards just here on Monday night. The Fred Thompson Courthouse. It's equivalent every year. It'll abate as much smog as 1,000 trees. So it's a pretty neat project. It's a neat thing. It's essentially a nanotechnology. We're introducing a very specialized titanium dioxide into those mixes to make it photocatalytic. And I talked a little bit about carbonation and how materials recarbonate. This is essentially the mechanism associated with that, right? So atmospheric CO2 reacts with the calcium hydroxide, which is in the concrete, and it produces more CaCO3. You're essentially making limestone on the surface of your concrete, right? And concrete actually gains weight as it absorbs the CO2 from the atmosphere. So like me, it tends to get heavier over time. All right? And then, of course, what we're here to talk about, nanotechnologies and nanomaterials for decarbonizing concrete. I am a student here on this. I don't know enough about it. And so I've been learning, and I've been finding out from the experts who understand this, and I'm excited to learn more from our speakers later today. So that's kind of the status quo. This is the new frontier, and this is a technology we should all understand.